Here I briefly give a few reminders on the complex plane. So this part is again only for ideal flow in planar 2D geometry. So we are dealing with planar flows and two-dimensional flow. And so let's consider our 2D plane. So this is the plane. Let's say this is the domain where there's a velocity field, but we're not thinking about the velocity at this point. We're just thinking about coordinates. So let's take a point here. This is our point. This is our position. Say we're interested in the velocity at this point, for instance. It doesn't really matter. And what you have seen before in mathematics is that you can think about every single point in the plane as a complex number. So you can think about this point x as a complex number z, right? Because you know that in 2D this point has Cartesian coordinates, that would be x and y, but you could also think about this point given its polar coordinates. That means r, which would be the distance to the origin, so this distance here, and the angle theta, right? And so if you are given a point x, you can think about the following complex number z, for which the real part is x, the component of your point in the x direction, and the imaginary part is y, right? So here the real part is x, and y here is the imaginary part. But equivalently, you can also think about this point in terms of its polar coordinate, and in that case, you're still looking at the same complex number, but you write it in exponential form, and r, so you know that x will be z will be equal to r exponential I theta, where r is the modulus of the complex number, and theta is the argument. And that leads to the same expression that we have when you go from Cartesian to polar coordinate, because exponential I theta is, so this is equal to r times exponential I theta, which is cosine theta, plus the imaginary number I times sine theta. So this is r cosine theta plus I times r sine theta. Okay, so again, so this is the complex plane. All right, and the reason why we're going to introduce the complex plane here is because there is a very, because of mathematical tricks, essentially. And that is, given the complex variable, you can define a function, let me call this function omega, as a function of the complex variable. So you could pick the function, for instance, z squared, right? You know what z squared is equal to. In terms of modulus and argument, z squared is going to be equal to r squared exponential I to theta, right? So this is exponential theta squared, right? So this is equal to r squared exponential 2I theta. So just like you define functions of the real variable t or x or y, you can also define, so note here it's a little bit tricky, z here does not represent the component along the z-axis. Z represents a complex number, but just like you can define functions of a real variable, you can also define functions of a complex variable, which is what we're doing here. So we're just saying we have a function which depends on z. And what happens, and this is a mathematical thing, is that functions of the z variable are automatically functions which satisfy the Laplace equation. So those, if you just simply write a function of z, you can think about this w as a potential which satisfies the Laplace equation. And that's precisely what we need for ideal flows, because ideal flows are flows that satisfy the Laplace equation, for which the potential, they derive from a potential, and the potential satisfies the Laplace equation.